Okay, good afternoon, morning, wherever you are. Good to everyone. Big welcome here from the DECT Forum to what is now the first of a series of webinars that we will run in 2025 on the topic of DECT NR+, following on to webinars that we've run over the last few years. And today I'm happy to say that we have Juho Pirskanen as the speaker, and Juho will talk about the release 2 of the standard. Juho is principal system engineer at Wirepass, and Juho has been active in NCTC DECT now for many years and a major contributor to the development of the NR+ standard. The webinar will be recorded and made available to everyone who is registered, and I'd also like to point to the FAQ page that we have on the DECT Forum website. There's one more thing, there's one additional person from Wirepass, Jari Hämäläinen, who's joined and who will be able to answer maybe some of the questions that, in case Juho cannot answer those. So with that, I hand over to you, Juho.
Okay, thank you very much, Roland, and hello everyone. Very happy to be here, and I'm pleased to present what we have done for the release 2. So, well, of course, as any technology standard, the development comes in series, and you try to leverage the possibilities that you have done in the previous releases and series of the standards, and typically not all the questions or all the needs can be addressed in single go, and rather you need to do multiple rounds, and this is now the second round of DECT NR+. So when we started to discuss quite many years ago, a few years ago already, that what would be the release 2 content and what kind of things we would be seeing, still the release 1 product development was ongoing, and the first products were, let's say, early, not yet even in the market, but they were coming to market. That was clear, but let's say starting in that phase to discuss that, okay, what can we do to improve it, and so forth. So basically the thinking was that let's build new functions that enable new use cases, which are perhaps somewhat limited in the release 1 and can be only partially done or not that optimally done, and then higher performance, of course, it's always good in the radio communications, and any technology that you can improve the performance of the system, and then also the easier to use and deploy, so that let's say in the first phase certain limitations are existing, and we are then opening or relieving those and removing those limitations. And also during that time when we were discussing, and now I think it was a wise decision that, okay, the utilize the release 1 capable chipsets, assume that we don't need to do any chipset upgrades unnecessary, and the release 1 chipset can be upgraded to release 2 simply by software, and maintain the full backward compatibility also to the release 1, so that there is new functionalities that are introduced to the standard, but the previous release devices can fully operate, and there's no this kind of discontinuity of the things, and things can with the release 1 deployments and products can continue, and you don't necessarily have to go to the release 2 immediately, but you can do that in the product different phases of the product implementation and utilization. So that was the big, let's say, the overall mindset of the release. Then what we did, basically, this is covering now the core specifications. Then we have the application profiles specifications separately, which we cover in the separate webinar. But when looking the core specifications from part 1 to part 5, and how the protocols are involved, what we introduced. So we introduced the support of very low power devices, so making possibility to implement devices that have very low power and really long battery time operation. We improved the downlink routing by 2 different features, which we look later more detailed. Secure joining and configuration data distribution. And we will look all of these features now a bit more detailed, and so that we can understand what this enables then for the products and different use cases. So basically, new use cases. So what we see, of course, that there is a possibility to introduce many new use cases when you have very low power devices. So energy consumption or current consumption of the device is very low. And what we did, basically, we looked at release 1 data transfer. I have sketched the figure explaining how the data transfer in high level goes in release 1. So basically, if you think about the device here in the left side, it basically, when it's not associated to any device, it's search for the network or search other devices, selects one for association, receives the cluster beacon messages and initiates the association, and then maintains the association towards that RDFT or RDFTPT device, so that it has the connectivity to the basically to the backend. And when the data uplink data, for example, comes to be sent, it can send the data immediately and get the acknowledgement, and there might be multiple data transfer. And if there's no more data, the maintaining of the association remains for the devices. So there's both directions, data going at any time. That can happen anytime, independently whether there is a data to send or receive. And of course, this is not optimum from few aspects from the energy consumption point of view. So basically, you have this association signaling, which is you need to do that, and then you need to maintain the association. And please look this aspect in release 2, that how we can optimize the process of the devices in release 2, so that if we have devices that are extremely power efficient. So the first one was thinking that, okay, many use cases that we envision, they could be water meters, smart device, or like the asset tracking devices, or other. I cannot name all potentials, but there could be devices that are sending uplink data mainly. The majority of the devices, they just send data. And simply sufficiently small amounts, and then they basically go to sleep. So basically now in release 2, the device is not associated. It's basically sleeping, completely off. It realized that it has something data to send to the uplink. It finds the network by receiving network beacons. It might receive multiple, but when it finds suitable, it can receive the cluster beacon as synchronized manner. So the network beacon contains the timing of the cluster beacon. So it gets all the necessary parameters with very efficient manner. Let's say the cluster beacon is 600 microseconds or roughly or smaller. in time, and then it can send immediately the application data and receive the acknowledgement. And then the router device or RDFTPT can then start routing the data to the backend. And when it gets the acknowledgement, it simply goes to the sleep. So now we have removed completely the association signaling and maintaining the association. And that enables the device going to the sleep. And the time that, if we think about that, the activity time, okay, it depends a little bit how fast the device happens to receive the network beacon, but after network beacon, the activity of the device is calculated in microseconds or few milliseconds to send the data, and that's the all activity that the device has. And if we think about that, if the device needs to send data to once to 5 minutes or once to 10 minutes or every 15 minutes, it basically sleeps the majority of the time, and that allows very long battery time operated devices. But at the same time, we realized also that, well, this is fine for that kind of devices which are sending only uplink data, but then there might be also on those devices periodically more seldom to receive some downlink commands, and also there might be devices that require more periodically downlink data to be sent. So then we were considering that how do we enable that one. So basically a bit more complex figure, but many times same thing. So basically we introduced the long-lasting associations where the device is not receiving basically anything. It initiates the associations and indicates that I'm sleeping now, so that the data from the back end can be routed to the correct RDFT or the router, and that device can buffer the data for downlink when that comes. And basically now device is then periodically asking from the router that, by the way, do you have anything for me? And if nothing, it goes to sleep. And that how often that polling is happening is dependent on the configuration. So you can have it asking like once a minute or like every few minutes or more frequently. For example, if the device has sent something in uplink, it could know from the protocol design point of view that there will be a response from the backend, so it can start keeping the association and keep when it has the sent the uplink data, it can keep asking the potential downlink data very efficiently. And then of course, if there's a multiple like a case that there's more data, the actual downlink transmission may take multiple transmissions. As similarly in the uplink case, that of course you without association you might do few transmissions in a row. And then of course, when putting everything together, the actual implementation of the device and the system may utilize all of these. So it may be in this kind of release one baseline operation, if there's a very heavy activity on certain case ongoing, it can maintain the full activity and be like in this baseline operation. It can turn itself to be in this uplink data transfer without association state, so that it's only sending the uplink, doesn't expect anything in downlink, or then it can actually do the association so that the downlink route and the routing towards the downlink data is possible, and get the downlink data and optimize the energy consumption of it is based on these different operation modes. And this is now enables very low battery operated non-router devices. So this is the feature that that of course it still doesn't directly impact to the router devices, but devices that are not routing the data. Then the optimizing the router power efficiency is the topic of its own. Okay, then we consider that performance, so the downlink routing improvements. So in the release 1, basically we were, let's say, cautious, I would say, and not to make too demanding, and assuming that the applications that we foresee in the first release are very heavily uplink oriented. So basically it operates with the selective flooding, and I have 2 figures which are try to simply illustrate what happens in selective flooding. So basically the sink here, or the RDFT device, is sending the data to this node, but it's also additional transmitting this node, and the destination is here in the end. So there's one unnecessary transmission. This node, of course, doesn't anymore send it to this one because it knows that this is not the destination, and there's nothing behind it. And here this node doesn't transmit it here. So there's one additional transmission from the sink, which, okay, it's not optimum, but basically the data goes to the same route as the uplink data would be going, so it goes reliable manner and doesn't require any knowledge of the routing, and it's immune to any mobility topics. But then if we look the lower part, we realize that when the node is in different locations, or the network is larger compared to this example, the number of unnecessary transmissions starts to grow. Because of course here it would these nodes would need to receive also until to this node, where they realize that actually there's no this destination behind me. And of course we expect that the need for more downlink capacity is needed in future, in coming years. There's more applications that would require bidirectional communication, and it would be good to have the improvement and how do we can restrict the flooding more. So the data itself goes to the best route towards the destination, but there's these unnecessary transmissions, which in the end is waste of energy and waste of radio capacity. And same time realizing that if you can restrict the flooding in the high in the downlink or in this cluster tree in the high level, it has the biggest impact. So we developed actually 2 different methods. So the first one was the routing, downlink routing based on the cached information. So this is completely now backward compatible. So basically it's simply notifying the specifications that or noting the specifications that based on the uplink traffic, the route, any router or RDFT or RDFT-PT can make the association that, okay, I'm receiving this data from this next this downlink node, and I should send, of course, the downlink packets to the same road, and so it makes the relation to how to route the downlink data from the uplink packets. As there's no additional signaling, it's completely backward compatible. Other nodes don't even realize that this kind of restriction, or the node is like making clever decision based on where the data should be routed. But of course, there's a limitations or topics that the implementation should carefully consider. So of course, the size of the cache, how much they use their memory on defining this these associations. So which data should go to the which direction, and also the aging of the information. So how long the information that certain route is valid should be used as any time moment, of course, there might be mobility happening in below the nodes in the cluster tree. So basically these are topics that the implementation should carefully consider. And of course, if there's no uplink traffic coming, or it has been so old that you cannot rely on anymore, you can always go back to the selective flooding and start pushing the data to the next hop. And what we foresee, of course, is that this works very nicely for the features where you have applications operating in, well, I would say typical internet manner, that the client would be sending something to the server and server would be responding immediately. And then, of course, the information, when the delay of the network is sufficiently small, the information in all the routers is just obtained because there was this uplink traffic. Or there's like a release one functionality, this end-to-end ARQ, where if you are sending uplink data, the protocol endpoint in the sink or in the gateway would be responding that which data it has been receiving correctly. So again, there would be like uplink data and immediate downlink responses. Then the second part, basically, for the improving the routing, was to introduce this selective source routing. So basically, in the selective source routing, the routing is basically based on the recording the cluster tree topology at the root. So basically, in this RDFT sink device or in the gateway device where there's more memory. So the topology is created based on the registration messages from the RDs. They don't necessarily have to be separate messages. The device may amend this registration as part of uplink data transfer. So when it's sending the uplink packet, it can introduce this additional few bytes of information for updating the registration. Basically, the RDFT appends the route to route the PDU packets with the known route towards the destination RD, and the nodes between doesn't have to do anything specific. They can look what is the route from the PDU content. So basically, there's a headers, additional headers. The drawback, of course, here is that the PDU size starts to grow because there are more addresses, and that's why we made it so that systems can limit the how many hops or how many hops from the root, so from the sink, this system is used. So it can be, for example, used for only 1 or 2 hops, and then the additional overhead based on the addresses is small, and also the signaling needs are less because the changes below this limit, if you are like behind, we go back to the example figure. So basically, if in this example we would be having a limit of 2 hops. So basically, this node moving from this node to this node, so moving below this line would not need to make any registration because the sink would be giving the command to send the or include the PDU structure so that the data would be coming to this point, and after that it would be either flood or based on the cached routing going. So it's a compromise based on the needed signaling for registrations and extending the PDU size for those needed addresses and keeping the system complex, less complex. So of course you could do the selective source routing to the very, very bitter end, but then supporting like 50 hops or 40 hops would come very, very difficult because then you would have extremely many registration messages and the PDU size would overhead would be increasing significantly. But nevertheless, that is possible, but I would expect that implementations make quite careful choice that they don't use it at that deep. And as said earlier, the main gain of restricting the flooding is in the high end of the tree. So if you need to transmit once in very low in the extra in the low in the tree, it doesn't really consume anything from the system capacity or the device side. Okay, then going to the configuration data distribution, which is basically providing means for configuring devices more carefully, so or better manner than in release 1 and more efficient manner. So many times what we see is that of course in IoT networks many devices in a single system may utilize the same configuration, or you have a few set of devices and you have like a few sets of configurations, but the configuration is not necessarily individual for each device for each device separate. And if that kind of configuration would be done so that device-specific request is sent from the device, and then we would see the response from the server, that would first introduce delay and consume unnecessary radio resources. And configuration can can define different application parameters. So you might have different, for example, reporting periods, whatever values your application is actually requiring for configuring the correct operation at that part of the network. And in next webinar, we will discuss more on how the IPv addresses are handled in DECT 2020 network and how that configuration is done. And that's part of the webinar. But this configuration data distribution is heavily used in this IPv6 address and prefix distribution. The basic idea of the configuration distribution is that it's for the large-scale mesh network and minimize the identical information delivery from backend to each device individually. Instead, the configuration is given to the radio RDFT to the sink, and then it starts coming down hop by hop. So basically, when this device has managed to request the data from the sink, it can start advertising that data to the next hop and so forth. Basically, the functionality is such that the RDFTs and RDFT-PTs advertise this application sequence number. Basically, it's just presenting that when the sequence number has changed, the configuration data has changed, and there's need for devices to request the new data. And the RDPT then requests the information, and then it can start distributing that in its own beacons. And what we have carefully done there is that it's identified with a certain endpoint, and then different this configuration data may compromise multiple application-specific data items. So even if you have like many different applications in your system, and all devices doesn't necessarily need to understand the data, what the configuration is done, they can distribute the data to the next host. And the devices who, when they have obtained it, they can find their own configuration from the this configuration dataset. So the configuration dataset itself can contain configuration for multiple applications. Okay, so that's the like efficiency and also the how to manage the system, and as I said, for IPv6 it's we utilize this for address resolution. Then the final topic for today is the easier for the deployment, and that's for the secure joining. So basically, in release 1, all the network was we have the possibility to cipher the Mac PDUs, all the Mac messages, all the beacons, and so forth with an integrity protect those. But devices that are not part of that network, they need to be pre-provisioned. And of course, there can be different ways of pre-provisioning. You could do it in the manufacturing or other means like NFC. But of course, this is not necessarily very optimum. And for example, using NFC or any other radio or cabling or such is not very nice in the end. Of course, you would like to see the situation where the device can be authenticated and joining to the network. And now in release 2, we have enabled that one. So basically, in secure joining, we enable the network to accept devices without security keys. So you can turn the device on for or the network in the states that it can start accepting those on your defined time. Then, of course, there is a minimum amount of MAC messages are sent without security, beaconing and association requests and responses for those devices that are not having the correct keys. And basically, the radio device initiates the authentication towards the network server or network authentication server. Signaling is transparent now for the actual authentication method. Actually, we have now started new work for defining like a default or like certain methods, but the current release 2 is open for any authentication what your application, for example, would like to use. There's different applications have already different ways of doing that. So this is transparent, so basically you can utilize your existing one. And then when the authentication is completed, network provision parameters and network security material are provided to the radio device. And then the device becomes the normal network. And the architecture goes like this. So basically we have here the client part who is trying to join to the network and to be authenticated. And then in the middle here, we have a device that enables that process. Okay, here is the mesh topology or multi-hop topology. And basically this proxy device is, so the client part here sends the messages to the proxy, and the proxy is forwarding those messages as normal uplink packets to the backend for the authentication. And the communication then happens between the client and the server. And the proxy device basically prohibits any other data going through than the packets related to that authentication process. When you do it once for multi-hopping, you can realize that actually the client server and this model is very easy for the star topology. So you basically have the client, and then you have the server, or basically the gateway and then the server. Of course, we haven't defined any restrictions where you are locating this authentication server. So we would of course expect that you have the like the sink and the gateway device, and then you have in your backend system you run some network management server, which is having the authentication server functionality, where you can do the authenticate the device that you are showing. And as said, the actual method is left now open. You can use the existing one or your own ones, or you can do your own. But now in release, or let's say we have started to work to define some methods, like make it like DECT specific, but we still believe that there is applications specific authentication methods which will remain there as de facto for those applications. So this like freedom of choice and freedom of using different methods is there. Okay. Actually, in short, this was the presentation now. Now there would be time for questions and comments, and we can try to answer those.
Maybe commercial question here from Jerry Lamotte. Worldwide, what is the status of the deployment of DECT NR Plus today? Are there any major up and running use cases? I don't know if that's something, Jari, you want to answer?
Yes, I can take that question. So, first of all, there are several companies working related to professional audio work in the DECT NR Plus, but from our company perspective, we are working in the industrial IoT, where we have actually many different companies in different branches working with the technology. We cannot close the commercial status of the operations deployment, but there are design houses, gateway providers, and industrial companies working on the NR Plus in different countries. For example, smart metering is in the energy sector one of the use cases. Street lighting and smart city application developers. Also the street lighting related topic in the sensoring area for the smart buildings, and also smart building emergency lighting. So that kind of companies, especially in the European Union area, but also India, North America. And to be noted that with the North America, there is need for the temporary FCC permission in order to go for the trialing of the NR Plus technology. Thank you.
Okay, thank you, Jari. Then we have another question, which is, how does the device avoid collision when sending data? And I'd ask
okay.
you.
Well, the avoiding collisions in generally. Well, we have in release 2, and release 1 already. We have basically 2 transmission methods defined. The first one is a random access type of transmissions, which as per se are random. And of course, there's a probability of collision. But we utilize the LPT, so listen before talk, or you could listen before talk, and to minimize collisions when there's somebody already transmitting. But as they are random transmissions, it's known that they are not collision free. But the protocol has designed so that it can recover from those potential transmission errors because of collisions. And then we have a second transmission method, which is scheduled transmission method, where the radio device in FT mode, whether it's having the backend connection or like a router, is scheduling and giving the resources for individual other RD in PT mode to receive and transmit. And then, of course, it's a scheduling algorithm decision by the FT side, how it wants to give which resources it would like to give. The signaling is quite flexible, but then, of course, the transmissions are not colliding or assumed to not to be colliding. Of course, you can make an incorrect implementation, but assuming that the implementation is correct, so that then individual transmissions are not colliding inside that inside that cluster or inside that perimeter of that RDFT. Of course, the DECT is operating, for example, in license exempt band, so you might have multiple systems, but we have been also trying to look very carefully that if you have multiple systems, that they can avoid operating in the same frequency channels and same frequency times, so that the collisions can be avoided also in those cases, or minimized at least in those cases.
Thanks very much, Juho. Here's another one. What is the maximum number of nodes supported in release 1 and release 2?
So in both cases, the maximum number of devices basically is limited by the radio device ID size, which is 32 bits, and it's a bit more than 4 billion. So we don't see that as a limiting factor at the moment. That's the theoretical. Okay, what is then the maximum that you would like to have in the single system is up to you, but in single system with multiple gateways, multiple sinks deployed, you can basically deploy 4 billion devices in the system. Okay, if you want to use multicasting, then you need to receive 4 multicast addresses from that 4 billion address space. Then in the single radio area, let's say, and having multiple, well, okay, that's then comes to we can recover from the case, but I would say that 56,000 short radio device IDs are available, and if you have higher number of that, then perhaps the performance is not always exactly optimum, but so that 56,000 devices would be hearing each other, but we have then, for example, in DECT channels, we would have 10 different channels, DECT band, 10 different channels. So even in that case, different channels devices operating with the same short radio IDs in different channels would not cause necessary problem. So I would say that those are the limitations. We don't have, let's say, any other, like the ID sizes are the minimum, or which are let's say restricting the device and the system size.
Okay, thanks for that elaborate answer, Juho. There's one more technical question, I think, or question for you at least. So the question is, my understanding was that release 2 key feature was IPv6 compliance for future plugin with app layers such as Matter. Is that IPv6 layer specified in this release 2?
Yes, so that's okay. Maybe I should have included that part also, but as we have the separate presentation. But the main point there is that this configuration data distribution is the enable for the IPv6 efficient IPv6 operation, and we have a separate application profile now available for IPv6. So which is part of this application profile. So we were intend to cover that as a separate part, but that's a separate TS which defines how you configure and how you obtain the IPv addresses and how you utilize IPv6 on top of DECT NR Plus network. And one of the functionalities that was seen necessary for that is the configuration data distribution. I will come, or we will present in the next topic how exactly the IPv6 then is supported.
Yeah.
In the application profiles presently.
You mean in the next webinar then, you all right?
Yes, next webinar, yes.
Yeah. Okay, well, I think we've come to that point now because that was the last question we received. Then I would just like to say that there is a next webinar already planned. Cannot give you an exact date, but expected in the first half of April. And of course, you will find out by the usual means, email or LinkedIn or the DECT Forum website. Okay, I just want to go back because there is one other question. So for devices using scheduled transmissions, how many devices can be supported per second?
Okay. Well, that is a tricky question, because it depends how often you need to make the device to transmit and what is the physical layer option that you are using. But let's make an assumption that you need to transmit once per 10 millisecond. Let's say, for example, audio frame or similar size. So in every 10 millisecond, and then the transmission length for that kind of data packets with the decent radio link would be like 400 microseconds, so one slot. And we use the basic numerology 1.7 megahertz channel. So then in 10 milliseconds there would be 24 channels. So in single channel you would be able to support 24 devices transmitting, or then 12 devices transmitting and receiving with the 10 millisecond periodicity. But of course, if your periodicity is 20 milliseconds, then your number of devices is doubled, because then you can make the devices to transmit every other frame.
Okay. Right, well, I think people are now coming in with additional questions, so I think we can carry on. We have until the full hour, so another 10 minutes. There's a question here. Hello, is it possible to support asymmetric key exchange for the joining instead of pre-shared keys?
So, as I said, the currently the secure joining is agnostic for the actual authentication method, and we are now starting the work that, let's say, we would, let's say, at least endorse some of the methods, and one of the topic is that whether we in the first part of that do the research key or then public and private key. From the release 2 technical standard point of view, from the protocol layers, public and private key authentication method can be supported. There's no, let's say, we don't recognize any issue on that.
Okay. Thanks. Then here's the last question, I think. What is the maximum data rate with version 2?
So we haven't implemented any new release or any new physical layer transmission modes in release 2. So the release 1, depending on the channel bandwidth is and the maximum modulation encoding that the chipset is using, is ranging from 1 megabit, I would say from 1 megabit to several gigabits. But of course, the current, what we see in the marketplace, current chipsets are operating between 1 to 3 megabits with 1.7 megahertz channel bandwidth. But by introducing a new chipset and which supports wider bandwidths, then of course the data rates will be high. But for the IoT, for example, use case, we see that this 1 to 3 megabits is quite nice at least this point of time. But
yeah. I believe so too. Yes. Okay. Thanks. Then, yeah. Just back to the next webinar again, first half of April, which will talk about the application profiles, which are now in development by, or at DECT. So I hope to see many of you joining that next meeting. And something else I want to bring to people's attention is that DECT Forum will be present at both the Embedded World event in Nuremberg from 11 to 13 March, and also at the Hanover Messe, which is 31st of March to 4th of April. So if you have the occasion, then please drop by and you can see demos and get further explanations about the technology. And that was the last thing I wanted to say. There are 2 additional questions, but I think we'll, unless you want to take those, Juho. There are 2 more questions. Is that okay? Or
Okay, we can take it. I have until the full hour time. We can go forward.
It's nice to see the engagement. I also see people are dropping off, but we'll carry on until Okay, so is there any improvements in transmit-receive mode switching delays in the physical layer firmware?
That is, we haven't changed the minimum requirement of the standard, but then of course that depends on the actual chipset implementation. I would assume that they improve by the time, but I cannot really comment.
No, okay. And then there was a follow-up question from Guus, aangenaamd on the data rate. He says, what is the maximum data rate with the NRF 9151 today? Is that something you can comment?
Perhaps you should refer Nordic datasets or ask directly from them. But my understanding is that it's around 3 megabits in physical layer, but you have to ask from them exactly.
As Nordic Semiconductor. Yeah. Okay. Fair enough. Thanks very much for that. Then we have really come to the end of the session. I would like to thank the speaker, Juho, for giving his excellent presentation, and Jari also for standing by and helping here with the questions. And of course, I'd like to thank all the participants for calling in today. There were more than 70 people at some stage, which shows that there's still a lot of interest for our webinars, and we hope to see you again in the next one. Thank you very much.